likely to be tensor of something by something by something.
I'm not even there. I'm like, I can, yeah, it's.
Yeah, it's pixelated in some low resolution.
Just increase the.
I'm trying to change the themes and such. Tell me if the light theme is better than the dark theme.
I think so, but like, still very pixelated for some reason.
It actually looks like the.
Oh, that's better.
Yeah, it's better. It looks like there's some progressive anti-aliasing thing that's not working or something. Anyway, it's slightly getting better. I can read this.
Yeah, this is fine.
Okay, that's probably as big as I can reasonably go. Okay, so this is the unidirectional LSTM model. So I'll just start kind of briefly at the top because it shows off some more interesting stuff than the, I think the ad or whatever that I had before did. So this is starting basically from the MLIR test that's checked in, with the assumption being that we've lowered it to HLO. And this is prior to running any HLO canonicalization or conversion. So there's tuples, which we need to get rid of because they're just a mess. It's a workaround for HLO not really supporting multiple return values and stuff. So you can see that there's giant swaths in places in here of just extracting tuples. This also has structured control flow in it still. So here's an HLO WAL with its loop condition as an outlined function and its body and stuff. So the first thing we need to do is kind of get that into a more reasonable form. And so through this process, we flatten tuples, we destructure the control flow. And yeah, here's where you see a whole bunch of these nice little tuple axes. So here, yeah. So now we're out of tuple land. So we have just a bunch of.
So Ben, just a comment about. I wasn't clear of how MLI is supposed to deal with it. So when you have to return, a function can return multiple values, right?
Yep.
But then the call operation is returning has multiple result values, and those need to be handled in some way.
They end up each of the result values ends up as a different SSA value, as opposed to if it was a tuple, it would end up as a single SSA value that then needs to be extracted.
Right. So you have like this #1, #2 kind of things, right? Or
correct.
Whatever that the symbol is. But at some point, when I was working on something related to affine maps, where affine maps could also have multiple results, Nicholas pointed me to some old thread that basically said we don't want to have multiple result values. So I don't know how that's going to work out eventually.
No, multiple result values are here to stay.
Yeah, that's.
Yeah. But you know, like the affine maps, like one of the things that I ran into was the affine maps was changed to basically make multiple return values. It is implemented in code, but is unsupported. So at some point you get some assertion saying I don't know what to do here. And it came down to basically the affine apply operation, which is an operation affine dialect, returning multiple values and that not being handled correctly. Somewhere in one of the pattern rewrite or conversion rewrite, somewhere I ran into
maybe we can follow up on that later since we're recording this, just to keep it focused.
Okay.
Yeah, that sounds affine specific, I think.
Yeah. So once we get out of tuple form and we have a bunch of nice SSA values, we've also switched to a real CFG here. So we have conned branches and basic blocks, no more structured control flow and HLO WALs. This makes it a lot easier to do kind of code motion stuff, as everything now is an SSA value without being hidden behind tuples and kind of wrapped in control flow and stuff. Let's see. There's a lot more to scroll through when it's giant piggy size. So when we're going into the flow dialect then, so we've kind of got our input dialect with all the HLO canonicalization performed. When we're going into the flow dialect, we first start to look for specific operations that we want to support before we go into a general conversion pass. And this runs as part of the pre-partitioning conversion. And here we're doing things like looking for variable loads, tensor readbacks. So this, for example, was the while loops comparison, determining if the while loop should terminate. And so here we've inserted where there is the compare, performing the actual comparison to see if the while loop should terminate. We now have this tensor load that's loading the actual comparison value from the tensor, and then switching on that with the conda branch. And through later lowerings, this will kind of be preserved. And what this indicates is if we were to naively run this compare, which is acting on tensors in an actual dispatch on, say, the GPU, this tensor load would be a readback onto the host of that tensor value, implying that there's a synchronization here that would be required and other kind of badness. So the nice thing is we now have a bit of IR that if we're looking through this, we can very clearly see where there's a data dependency from the device to the host. And kind of one of the goals later this year will basically be to remove as many of these as possible, because these are kind of the badness. And the kind of thing that we really should be doing here is going through the HLO, and for things that don't need to be tensors, making them not tensors. So for example, this comparison does not need to be a tensor. The value that it's acting on here is a scalar that is produced effectively on the host and consumed effectively on the host and never used on the device itself. So it's silly to be running this as something on the GPU, for example. So if we do that purely in the HLO space, converting these kind of scalar operations that are unidirectionally host to device to actual scalar operations, then we kind of avoid all of these round trips in a lot of cases. Let's see. I guess I should just search for IR dump after. Yeah, so this now, these are starting to identify dispatch regions. And so this is finding the HLO ops that are acting on tensors. So for example, here's that compare, and moving them into these dispatch regions, which are just kind of nested, explicitly capturing regions. So this is capturing the arguments to the function and then remapping them, performing the comparison, and then returning, and then bouncing that back. So this kind of transformation is purely reversible. It's just done here to start to isolate what we actually want to dispatch and execute on a device versus what is host code scheduling the dispatch. So here's the interesting one, because this is the main function now. So you'll see some of these dispatch regions have a single op, some of them have many. This is based on kind of the current very naive heuristics that are looking at kind of the number of invocations required, if you're thinking of this in a SIMT model, to perform this work. So here, this requires 10, and that's really today because of the naive logic, just because the output shape has 10 elements. And this requires 320 because this has 320 elements. There's a lot more sophisticated stuff that should be done here. So for example, if, say, this broadcast is used by multiple different ops that end up in different regions today, this will run as its own region, which will then have that value flow in. This is probably consumed by one of these arguments way on the side. But really, this broadcast is kind of a free operation, and instead should be materialized multiple times and put into the dispatch regions that use it, so that we aren't going from a single scalar to a 10-element tensor in this place to then just pass it in where it could otherwise be free. So there's a bunch of different kind of optimizations we can do there, with the goal being the fewer dispatch regions we have, the less overhead, because obviously we're doing less work, we're fewer dispatches. But also we now have fewer tensors that actually need to be materialized, because anything that flows between these dispatch regions is effectively an allocation that has to exist at some point in time to carry the data between the regions. Whereas if this broadcast, for example, was inside of this region, now that value never needs to live outside of the region, and it can effectively just be hidden. So, you know, right now there's other things like reductions are currently put on their own, but that's something we'll want to fix as well, because you should be able to fuse a reduce and a broadcast together, for example. We do some stuff, so maybe one of these actually has a better example. Probably not. So we do try to move constants into dispatch regions if they would otherwise be captured. I don't know if any of these actually demonstrate that, because the original model was kind of written to support this. But the basic idea there is the fewer things that we have as constants that live outside of dispatch regions that we can move into the dispatch regions, again, the fewer things we actually have to materialize, the fewer bits of data that we actually have to provide at runtime. So we do that. CSE runs, we run that frequently through this process because, and that's common sub-expression elimination. So that's if you have like two bits of IR doing the same thing, they're deduped effectively up an entire tree. Constants. Yeah, so now what we do after we've done a bunch of these kind of CSE operations and canonicalization to kind of clean some of this stuff up, is we go and try to fold dispatch regions that now are compatible. And this is kind of an example, as Sean likes to call it, the global versus local transformation. We were performing a bunch of local transformations of kind of individually for a set of ops, putting those into a dispatch region, individually for a dispatch region, moving constants inside of it and out of the outer scope. And now we can kind of look at the whole function after CSE and say, okay, now are there any dispatch regions that themselves can fold together through those? And so that's just, again, is kind of like a nice way to just continually try to merge these dispatch regions and reduce the total count. I wish I had disabled threading for this so that it wasn't running the same pass on multiple functions all over the place. Yeah, and so then this is the big one, the kind of getting near the end of the flow dialect. This is where those dispatch regions now get outlined into executables. So these would have been the contents of the dispatch regions themselves. And now all of those dispatch regions just became dispatch calls referencing those executable functions. And the idea here is, these passes don't exist yet, is we can now duplicate these executables. So if, for example, you had a bunch of library calls originally on the Python side that ended up generating a lot of these things, you're likely in a very large model to end up with a lot of these that are similar or identical. And now that we've outlined these, we can kind of look across that. And even if there's hundreds of functions that are calling these dispatch regions now, we can perform this very isolated transformation of basically find executables with the same contents effectively, and dedupe them. And none of this code really changes. It changes the executable it's referencing. And so we kind of have this nice isolated transformation that kind of works there. The other thing we can do is merge these executables together. So again, if right now a lot of the backends are relying on there not being multiple functions, and so inlining is running very aggressively. And so all of these are effectively just a single function. But really, we don't want that in terms of our kind of code size for deployment. We want as much reuse as possible of a lot of this stuff. And so ideally, there would be multiple functions in these executables sharing some code, and there might be multiple entry points into those executables. You might have function A and function B exported that both themselves call an internal function C. today that's not modeled correctly. But we should be able to do that. And that on backends that we can get benefit directly at runtime from that. So for example, like if we were lowering this to LVMIR and then actually generating code for that, we get the code size reduction, and then at runtime, it's all great. SPIR-V, there is no linkage between different like Vulkan pipelines. And so you would still, even if there were two exported functions in here sharing the code on disk, you would be getting a disk savings. But you would still have to materialize two different pipelines fully compiled with the same content. So at runtime, you would not be reducing the number of compilations you had to perform. And there are some ways around that, but mostly that's just unfortunately the way things go there. As mentioned, that tensor load still exists. So what was the compare and then the load of the tensor is now the dispatch to the executable that's performing the comparison and load. So again, we have a nice place where we can kind of see that like here is a data dependency between some operation that's being dispatched and the actual data being loaded. And that's the badness. That's what we want to get rid of. We do some more final conversion. So there are some ops that, for example, like dynamic update slice, which I don't think this model uses. Oh, actually it does. So those get turned into flow tensor updates. And so instead of modeling dynamic update slice as a dispatch region, we look for them specifically here and pull them out, because now we can actually reason about what these are doing with their kind of in-place updates. And that will make further transformations as we go down to the HAL dialect easier. If it was just a dispatch, we wouldn't know the semantics of the operation here. Whereas here now, we know that we're only dirtying a very specific part of the tensor we're writing into. And the tensor we're sourcing from is a much smaller region than if we were just looking at the entire contents of what we were putting in there. This is another example of the readback as well. So here, I think this is reading possibly the loop index, and then using that to index in and store this LSTM iteration time step result. Again, that loop index doesn't need to be on the device at all. And if this was on the host, there wouldn't be this readback here, and then the whole thing would happen without readbacks. So it's another reason to get rid of those sooner rather than later. Let's see. Now we start to, so we've got all these dispatches. We need to start to, and by creating those dispatches, we've gone from a whole bunch of ops, the original model to basically these kind of opaque dispatches that capture some arguments and return some values. And here's kind of like multiple returns, as some of these return multiple tensors. And through that, we've kind of hidden a lot of the complexity that happens inside of there now. Like we've removed any of the allocations effectively from the scheduler's visibility that happen inside of those dispatch regions. Like we don't care if those are going to LVMIR, which is then doing stack allocations for some stack variables, or they're using shared workspace memory on the GPU or whatever. From the scheduler's perspective, they have what they need. And so now we want to go the next level in the hierarchy, which is between these dispatch regions, figuring out what the scheduler actually needs to be aware of. And that's where kind of the stream formation comes in. Let's go to, yeah. So this one starts to get more interesting. So here we had all these dispatch calls. For the stream formation today, it's extremely simple, and it's only acting in individual fragments within basic blocks. So you see there's this basic block jump because it's part of a loop. And so there's a stream fragment here, and then there's a stream fragment here. Ideally, we would be stitching those fragments together across the blocks. But today you just kind of see this. But what this is modeling then is that these explicit captures here, of which some of these are workload sizes for dispatches, others are tensors. they will be soon shapes. So shapes will be able to be captured here, shape dimensions. Once we're inside of this stream fragment here, the explicit captures that we have are the only things that are required to begin the processing of all of these operations, and the results of them, of the stream, is the only thing that then now is visible at the top level scheduling. The transient tensors that exist in here between these dispatches that then are mostly flowing to these other dispatches are now considered kind of unimportant from the scheduling perspective. The stream, and this kind of gets into the following lowerings, however the stream lowered to the HAL dialect wants to allocate and deal with these tensors is now completely up to it. The scheduler at the high level doesn't need to think about how it's going to allocate this buffer. Well, this one in particular leaves the stream, so that's kind of different. But if one of these didn't, so like 40#0, for example, doesn't leave the stream, that now lives entirely within the stream. And if the stream wants to put that in a ring buffer such that the actual contents of that are only ever in existence for the dispatches that require it, it's now able to do that. It's also able to look at this, and given the synchronization boundaries, it knows that any operation that was computing these input values, not these constants, because that's easy, but like say the actual input to the function here, arg0 has to be ready and computed and available before any of these operations in the stream can begin. And it's the same for all these other ones. So they need all of their inputs to be available before they begin. And that gives us a nice coarse boundary where within the stream fragment, we can think about the order that these dispatches need to go in based on their SSA value dependencies. And then between the fragments, we can think about the order the fragments need to go in based on the order of their SSA value dependencies. And so we've kind of split that problem and divided it, applying the same kind of logic to both, but now with some different semantics based on what we want.
Is there anything that can prevent us from putting all dispatches in a single basic block into a single stream fragment?
Yes, this right here. So here's our data dependency. So it has to run this dispatch, and then it loads that value back on the host, and that value itself is then passed in somewhere in this giant list into this stream fragment. So, and this is where if this value was computed on the host, then these could be merged together because they wouldn't have that dependency. But this is basically when we start to think about what a host synchronization round trip is, this is basically what that looks like.
So that %28 is used to calculate like the workload or some other sort of host necessary value?
Yeah, so that comes in arg16. So I'm going to guess that's right here. So it's used in these tensor updates, which are the dynamic update slices, to compute the index where it should update. And that's kind of nice because these tensor updates are within the stream. And so all those things that I mentioned about being able to kind of only keep, in this case, these two results of this dispatch here, the 44, 3, and 2, are only used to update that tensor. And so if those were allocated in a ring buffer, then this just becomes a copy from the ring buffer to this target. Or ideally, they just, the allocator would get the view of the memory for this target and then directly write the results into that. But we've been able to do that now at like a very local level instead of having to think about the whole program because we've isolated that in this fragment. Yeah. You can trivially see this doesn't escape and etc.
I really like this, Ben, because here in the IR, down the road when we're optimizing, you can come and just trivially see a lot of these issues, and we can be like, well, how do we fix that? Well, what's that loading? And kind of look in our locations, go back, and then sort of, be like, oh yeah, well, this is because we're actually doing I++ in HLO or in the dispatch region or whatever.
Yep. Yeah, that was kind of the hope, is that we would have nice big red flags very early in the process, and we can emit performance warnings and all that kind of stuff here. This still is correct, and it will do the right thing, but of course it's not what you really want. And there's other things we can do. So just like these tensor updates are moved into the stream fragments, we could, in some cases, move these loads into the streams as well, if the usage of them is able to be handled at runtime. And so an example of that is if the value was just used for the dispatch invocation count, there's an indirect dispatch that we can use as an indirect dispatch is basically, instead of saying a dispatch that requires X number of invocations or XYZ grid size, source the XYZ grid size number of invocations from another buffer, in which case this tensor load and then this dispatch would basically be canonicalized together. The load would go away, and instead what we're loading from this buffer here would be used itself as the dispatch workload argument in here. And so this is an example of, due to the semantics of Vulkan, we can't really do command buffer recordings of copies with indirect arguments yet, and so there's 6 here. But there's other workarounds for this that even in the case of us not being able to, like maybe this comes from a custom op that is running on the CPU, and we just can't eliminate that. We might be able to still record this buffer and dispatch it without having to wait for the host to be complete. After this, it's mostly magic reflection information gathering. We're mostly done with the flow dialect here, and we want to get all of the reflection information that has the nice typings on these tensors and their shapes and everything before we start to remove the tensors and the shapes that we actually need to generate that. So if what you want to do is match the original source language Python, for example, calling semantics into this model, this is kind of the last chance that we have to do that. And we want to do it here rather than earlier in the process, because now we've done all this inlining and type conversion and hopefully a bunch of other magic, such that the contents of this will likely be very different. And compared to what it was above, where it was a couple dozen functions, after we run symbol DCE here, we basically have a single function. And so we didn't have to generate a bunch of reflection metadata for all the other stuff. Okay, and now we get into the HAL stuff. So we have this function that is most of the unidirectional LSTM with the streams, with dispatches. It does have the control flow in here, so this is its while loop and the loop iterator and stuff. And then all of the dispatch regions have been outlined to executables. And so like here, for example, is a pretty beefy one. This is probably like most of the LSTM, given the TAN-H's. But this is a majority of the logic just lives in here now. And so this kind of getting to the difference between scheduling and execution. The scheduling logic here is what you need to schedule only. So it's some constants that are the indices. There will be shapes out here, shape dimensions. If there's any control flow that's not tensor based, it would be here as well. Whereas the stuff actually acting on the tensors is the stuff that's now been put into the execution side. Now, as we start to go into the HAL dialect land, the first thing that we're doing now, and some of this is like just within the last couple of weeks, so it's actually kind of nice that there was a little break there. So what we need to start to do now is, for these executables, start to really build a concrete representation of what their interface looks like to the various systems that are going to be interacting with these executables. And that means both the scheduling side, trying to emit the HAL API, which is very Vulkan-like, and how does Vulkan reason about these kind of interfaces? How does it pass values in and get values out, et cetera? And then the various backends as we're lowering into them, because they all have very different semantics. The LVM JIT backend will end up with very different semantics than the Vulkan backend, because they're obviously completely different systems. And both of those will end up very different than VMLA, which is using the IREE VM, which then itself has very different semantics. And so the goal here today is just to model what we have. And so this is like 0 through n for each argument. Here's the two original function arguments and the original function result. So that's what you get. But this will end up getting much more complex. And the primary reason for that is that we have a very limited number of these bindings that we can have. Basically, if you think of each tensor ending up as some buffer, and then us needing to provide a buffer binding for each of those. In a lot of cases, we may only have 8, and in the most usable form with dynamic offsets, we may only have 4, which, if you were to naively be doing this, means you can pass in and return at most 4 tensors from any one of these dispatch regions, which obviously sucks. So the idea with the interfaces here is that the bindings that exist here will not be one-to-one with the arguments and results of the functions, but instead one of these bindings might contain multiple inputs to the function. And it's the job of the scheduler to allocate and put those in the right form such that the actual dispatch region doesn't care. What it ends up doing is saying, load me a tensor from this binding at some byte offset. And the scheduler will provide the byte offset, and the scheduler will provide the binding. And what the code was in here, which was basically just a function with arg0 and arg1 and returning a result, is now still doing effectively the same thing. In fact, the way I do this is I just create this thunk function that does these tensor loads and stores, and here was the original function with the arg0 and arg1. So this is what originally it looked like, and now we've kind of added this interface layer of indirection such that we can do this kind of manipulation where we're loading from offsets and storing to offsets. But the rest of the function and the rest of the code gen lowering, for example, doesn't need to think about any of this. It just thinks as it would look at any other function that it's lowering. And so this is where we get like a really nice separation from what is IREE specific, which is really this, to what is kind of generic code gen on TensorE things, which is the original function here. And the other thing that this will do, and this is some of the CLs that I am currently working on, is instead of just loading tensors, you'll also be able to load little constant values. And so you can load, for example, like an index. And so when we get dynamic shapes, dynamic shape dimensions, so the actual dimension values that are themselves dynamic, can be loaded like this. And so we'll then be able to do things like tie the shapes together, for example, of tensor 0 with a shape computed from this index that was loaded as one of these kind of runtime constant values. So that is hopefully coming in a couple days, and that gets us across this boundary. Because these are nice generic kind of things here, depending on the backend that you're lowering into, they can do different things. So Vulkan, for example, most of these constants that we're going to be moving across the boundary here will end up as push constants, which are effectively just a way to embed registers directly in the command buffer that then can be loaded for free effectively in the shader. Or we might spill to uniform buffers where if the scheduler runs out of the maximum number of push constants it can use, so say you have a ton of dynamic dimensions or a ton of kind of specialization values you want to pass in, they can spill those into a ring buffer with a uniform buffer that would just appear as another binding in this list, and it would appear as a load of like an int32 or an index from a buffer at some offset. But again, the code that was originally there and the code gen backends, for the most part, don't need to think about any of that. They just need to be able to translate these couple generic functions to whatever they actually need to do. So yeah, all these now have interfaces. Oh, either that was the end of this file. Yeah, that was the end of this file. So I kind of randomly captured from various output states. So the next thing that's done is we have those interfaces, and so those interfaces do model HAL structures. So like this, these sets and bindings are kind of, all of this terminology comes from Vulkan itself. So they have descriptor sets, and a descriptor in the Vulkan world is basically like just a pointer to a buffer. that might have an offset and a length and something like that. And you organize your pointers to buffers into descriptor sets, of which there could be multiple bindings. So binding 0, 1, and 2 of set 0. This is one descriptor set, basically. So one set of descriptors that are representing the bindings. You can also have multiple sets. And so there's no reason, and in the future we will have things like this. Now there's 2 descriptor sets, one which has 2 bindings and one which has 1. And the reason you normally do this is updating these descriptor sets is not cheap. And it's something that you have to be very careful about what you do when you're scheduling these things asynchronously. And so normally what you try to do is divide your bindings up by which the frequency at which you're updating them. So for example, in a world where most of the transient buffers that are living inside of these kind of streams are only used within those streams, most of them will be allocated from like a bump pointer ring buffer style big slab allocator with a base offset, and then each dispatch will be getting a different byte offset in there. And so we only need to create and update the descriptor set that points at the base of the ring buffer once, and then we don't really need to change it again. Whereas if there are tensors coming in as function call arguments where we don't know where they come from, they could be in a ring buffer, or they could be passed in by the user or returned by a custom op doing its own allocation. Those might get updated much more frequently. And so we can put those in a different set. And a lot of dispatches might not have any at all because they might only be using the transient buffers, and that's really nice. And then other ones will. And so we're only paying for the extra cost of updating those descriptor sets when we need it. And we have kind of a good way to organize that. So this is still pretty new, but now one of the things that actually costs a lot of time at runtime when you're doing these kind of descriptor setty things is caching them. Because you really want to, given the expense of creating them. And so a lot of runtime systems that deal with this end up with big hash tables that try to hash all of the potential states. So like they'll have hash functions on all this kind of stuff and the buffer pointers that are currently in use and all these things. But we can do better than that because we can just code gen all of this. And so what normally is a hashing operation on these and a hash map lookup every single time you want to do one of these operations. Instead, I'm just materializing global variables for each unique one that we have, deduplicating across all of them, and then initializing those at startup. And so any place that needs these, which we'll see if I can actually find the real code here. Yeah, any place that needs one of these layouts is now just directly loading this variable, which at runtime, this just becomes literally an index into an array, and it's free. So this is an example of where through the code gen and through being able to look at this like IR and getting whole program visibility, we can eliminate entire classes of work that would traditionally need to be done at runtime. And it's the same with kind of executable caching. So we need to cache at runtime the executables that we're actually compiling, because this is taking the SPIR-V IR or LVM IR into its actual JITted generated driver handle or function pointer through the LVM JIT. And we want to cache that. Again, instead of needing a big cache infrastructure, we can literally have a variable that is the cached thing, and we just load that and use it. So again, a whole class of kind of runtime related work that now doesn't need to exist. And this kind of big block that I was scrolling over, there's no load store forwarding on any of these. And so there's a whole bunch of redundant loads and stores. This is kind of the initializing the executable cache and compiling everything. This really needs to be cleaned up, but that's separate from all this. Let's see, did we already? Yeah, so then it looks like here, somewhere between these two files, this also performed the executable translation. So I'm targeting in this particular run, wow, what that was, the VMLA backend. And so for this executable that already had its interface defined and had its original contents, it lowered that to the VMLA dialect and then to the VM dialect. And so here's the actual VM operations representing this min reduction operation. This kind of a bad example because simple DC hasn't run, so this function is not really needed for anything. But you can see the things that we're trying to load bindings from the interface become bindings to the interface. We get buffer views. We allocate a transient buffer. We perform the min operation. We get the output binding and we store it back via copy. And that's because the allocator is super naive now. Really, this shouldn't be an alloc. It should just be writing into the binding, but that's a separate thing. But basically what was the original stuff has now been lowered down to this target-specific VMLA stuff. We have that still in the same IR. So as we're scrolling through here, here's scheduling stuff that's happening at initialization right next to the embedded contents. And if we were targeting SpearV, this would be an SPV module containing the SpearV module. And here's the function doing the actual scheduling for that. So this is some of these things, so ignore these, defer release, but this is kind of computing the buffer size, allocating it, beginning a command buffer. This is what was represented as the stream, is command buffer begin. It allocates the transient tensors, which again, these will come from a ring buffer when we have them. It pushes the bindings. So now we know exactly what buffers are going to be bound and which byte range of those buffers will be used. And then it performs the dispatch. And so this workload, which is 111, is what's needed to perform the single min operation. And then we insert a memory barrier so that any subsequent operations after the dispatch can see the results of that dispatch. And this is an example of today, I'm not doing any kind of barrier planning. And so not only is this barrier not needed because then we immediately end the command buffer and don't record anything else into it. So this is kind of a no-op. These should only be inserted where they're actually required based on the data flow that we had in the flow dialect. Right now, I just insert them after every single dispatch just for correctness. But that's the other nice thing about having all of this in IR is normally inserting these barriers at runtime. If you were strictly thinking of a system that was just dispatching work, you would yet again have state caches for your bindings to make, because calling this, actually performing this, goes down to a Vulkan API call, which then goes into the driver, which then puts stuff in the command buffer, et cetera, et cetera. So not doing this work if you don't need to is pretty important, enough so that every runtime system includes look-aside caches and state caches to try to determine if it already told the API effectively that this has happened. But here in IR, we can trivially look at that. Like we, as a canonicalization, for any one of these push descriptor sets, look at the command buffer and see if there was a previous push descriptor set with the same thing and elide the ones that aren't required. And then at runtime, there is no need for any of that state cache look-aside or lookup. Same with the barriers. Knowing when to insert a barrier is super important because this is the kind of thing that controls your concurrency. If you have two dispatches that are completely independent, touching completely different buffers, and you don't have a barrier there, as you shouldn't, they can, in theory, if the machine is capable of it, run completely in parallel with no synchronization between them, which is great. If you insert a barrier there, though, when there doesn't need to be one, you've effectively removed the entire ability for there to be any concurrency between those two. So it's really important to get right for correctness, because if there were dependencies and you didn't have a barrier, they'll stomp on each other's memory, just like, you know, if you were writing a multi-threaded program without any locks or whatever. And so it's needed for correctness, but you really don't want it when you don't need it. And so here, again, by looking at the IR, we can omit them correctly in the first place, so unlike here, but then also perform the canonicalizations to locally inspect and detect whether some of these barriers are redundant or not, or if the scope of the barrier can be moved back a bit. So like right now, these barriers are full barriers, which say basically from the time this dispatch is performed, which is what this means, the dispatch has been performed and has completed and all of its results are written, to the very next time that we issue a dispatch, they need to be synchronized. But that's not always the case. So for example, if we were performing a dispatch that then was producing a result that we were using as an indirect dispatch to another dispatch, we wouldn't have to wait for the full thing to complete or wait until the command is actually issued. We can insert a memory barrier only there. So there's other kind of optimizations that we can do because we're looking at this whole program, and we can see exactly what the usage of all of these values are. Let's see where the tensor load ended up. Oh, that's going to be hard to find in here because I don't know what it actually became. Okay, well, we'll ignore that. So here's just another one. This is one of the super dense executables. You can see it's allocating all these transient buffers. That's just because I don't have an allocator in yet. But you can see how trivial it would be to elide almost all of these, in that the values that are returned from these are almost only ever used by the next subsequent operation and then disposed. So these should all just be fixed up. So it's low-hanging fruit. And then what that becomes then is basically just a bunch of function calls out to the predefined kernels, in this case, for element-wise add and mul and broadcast and such. Which, when you think about the overhead involved in a traditional system of doing these kind of library calls out, you usually, the first thing you do is you have a giant switch of like, okay, well, what are the types that I'm dealing with? What are the shapes I'm dealing with? What are the ranks, et cetera, et cetera? Where this is literally just passing byte buffers to a function that can, given the buffers, it already knows the type because we've already specified that. It doesn't have to deal with any allocations because those are happening in here. And if we improve the compiler to allow these allocations, then all that goes away. And so you can start to see how we're basically just calling functions, and those functions have a relatively small interface. They're not taking giant context structures with a whole bunch of additional information. They're only taking explicitly what they need, which is really, in this case, just the input and output buffers. More. That's most of the HAL right now. So there's more stuff like the ring buffer kind of modeled in IR will be one of the most important things for the HAL, because that's what will let us get rid of a lot of the allocations that happen in here. Some of these things, there's no canonicalizers yet. So this allocator compute range, we know at this point, we as the scheduler here, what the layout of these buffers will be. And that layout of the buffer might actually be determined at runtime, but we know at this point if two buffers were allocated from the same allocator and would have the same layout. And so we can start to use that information to elide some of these operations, where if we knew at this point, based on our compilation target, that this buffer was, say, always allocated with a dense layout, then we have our shape information here. This is 5 by 1 by 10. And the element size of the buffer, and we know its type. So we can just turn this into a constant computation. And if these weren't constant values, so this was some computed value from a dynamic shape, we could turn that into the multiplies and stuff and generate the IR to perform it without needing to make the call to the allocator's compute range. Whereas if this was a heterogeneous build, or a build where we might be targeting a backend that can have arbitrary buffer sizes based on, I don't know, your page size or something, whatever, that can be left in and then computed at runtime. Let's see. It's too far. Yeah, so this is kind of the end of the HAL dialect. Again, there's a bunch of optimizations we can do, but we now have represented effectively what would be the Vulkan calls. Like this command buffer push descriptor set maps to the Vulkan VK CMD push descriptor set. Dispatches VK CMD dispatch, execution variable. Like all of these things are effectively one-to-one with the Vulkan calls you make. So if you look at what we're actually doing here in terms of the amount of overhead, we're computing some sizes, which again, these should be constant propagated or at least emitted as IR. We're making the exact minimum, in theory, if we were aligning all the execution barriers, exact minimum number of calls to Vulkan that you need to perform the work. Any of the caching work that was done is gone. These are basically copying. These are basically just indexes into an array of allocated values. And so there's really not much else you can get rid of here and still have a functioning program. And so what's interesting is if we were to lower this to LVMIR, that then was getting generated to then call into the Vulkan API calls, there is nothing less you can do and still be making Vulkan API calls, which I think is like kind of the whole point once we get to this level is like there's nothing for the runtime to do because all it's literally doing is passing function arguments around. And the extent to which you need runtime support is for moving those values around is really based on your target configuration. So for example, if you wanted to take this form and then take that to a very specific target where you weren't using Vulkan, you were using LVM to go to the CPU and you were doing ahead of time compilation, things like these dispatches become enqueuing operations on a work queue. And so you don't need to go through multiple layers of indirection in a Vulkan like API and stuff like that. This dispatch effectively could become like a push onto a work queue. Or if you weren't having any threading at all and you wanted to run all of this stuff synchronously, this dispatch can become a literal function call into your actual compiled executables. So there's many levels to go from here. But we've kind of used the IR in this form to get to something that is kind of the minimal set. And inspectably minimal. Like I, as someone who knows what the Vulkan APIs are, can look at this and be like, okay, there's nothing else that I would do here as a human if I was doing this. Whereas here, it's like, oh, we're doing a copy buffer. Like, do I really need to be doing that? And in this case, no, because instead of allocating a new allocation to copy into, it should have placed that there to begin with. But that's something really easy to see at this point in time and trace that back to where that originated from in the flow dialect, where that was a flow tensor update, because this was the dynamic update slice. After that, we start lowering into the VM. So that transformation is pretty simple. So the IREE VM is basically just a very simplified version of the MLIR, I guess what you would call the execution model if it had one. So things like std.add_i to add scalar integers becomes a vm.add.i32 or whatever. There's a pretty direct mapping. And so like constant becomes constant, call becomes a call. The goal here was basically to make it require as little processing as possible to get in this form.
Hey Ben, can you talk about the things that the VM adds that are kind of not part of this, specifically type system and reference types and things like that are fairly important?
Yes. So one of the goals of having our own little VM dialect here, even like there is the IREE interpreter, which can interpret this VM as bytecode effectively, which is nice because it gets us dynamic deployment and things and you can load. But the other thing that this gets us is a lot of type aware operations now have, like we have a strict resource tracking model here, which models kind of Apple's ARC style. So we know that there will never be a null pointer. We know that if we're calling a custom function, which this model effectively does, because the HAL itself is implemented as a VM module. So this VM call here is no different than if you were creating your own custom module with your own functions. And the implementation here can now be strongly typed to take and return these types. We can verify that those types are registered at runtime. And so that kind of gives us this set where even if the next thing we do with this is lower these VM ops to LLVMIR and then generate code from it, and then at runtime we don't have an interpreter doing all this, we can still omit the code as we're lowering to do these type checks. Like we have the place we need them. We have the canonicalizations here that make them trivial to kind of alive when we don't need them or dedupe, which is much harder once you go to arbitrary LLVM form and get element pointers and kind of aliasing and all that kind of stuff. Because effectively here, we're still SSA form, not effectively, we are still SSA form IR with all these values, and there is no raw pointer access. So you don't need general alias analysis to do anything useful. The thing that we can do, and it's possible to code gen for this, but a little bit trickier when we're running the interpreter here, is if you're thinking of execution basically running from op to op as these are all being evaluated at runtime, we're our own little interpreter. We have our own stack. And so at any point in here, we can effectively yield the VM and return to the calling application. And then at some point in the future, continue execution within here, which is, again, you can generate code, and there's a bunch of like coroutine helpers and libraries and ways for doing this kind of stuff. But what this lets us do is if one of these calls, for example, might block, so this might be something that's a custom op that a user has defined that might be performing file IO, or it's, pretty sure it's somewhere in here, like a HAL call to wait for the device to be idle. That would block. Instead of literally blocking your main thread, here, submit and wait. So what the submit and wait will do is block the calling thread until the GPU is done and then continue. Which basically now, if you're thinking of this model executing, you've now severely limited your concurrency, because now no other work can be scheduled on the GPU while this thing is sitting here and waiting. But instead, if we yielded here, basically allowed other models, either other models that are loaded or the same model, to come back in and begin executing this code again. So like say, you know, in this stupid min reduction, I don't know why this keeps showing up. Hopefully one of these is more useful. Yeah, sure. So this one. So this is like per time step coming in. Let's say you're processing audio frames or audio packets. When you enter this function with a new audio packet, we can trivially tell at this point, because again, we don't need this complex alias analysis and stuff, that none of this work in here is dependent on any previous work that had been done in this model. There's no state here, because if there was state, there would be like a VM global ref load or something like that. So we basically know there's no way for any previous invocation of this to have a dependency that moves forward, which means we could continue building all of the command buffers here and recording them and sending them down to Vulkan, putting them in the work queues to go until we hit the submit and wait. And so what's great about that then is that if we yield here and then begin the next invocation for the next audio packet, we can get 2 now sitting and waiting for the device to finish. And if we queue another audio packet, we can get 3 waiting for the device to finish. And as soon as they do start to finish and we start resuming these, then they can continue. And so it's a way where normally you can't think about this, because if your entry point to the model in like a classic TensorFlow session run is there, those always effectively block. And if there is internal concurrency there, it's usually at a very coarse level, where here we can be continuing to feed the pipeline on the GPU or accelerator or CPU thread pool, for example, without actually limiting ourselves based on this kind of false dependency. And there's more useful examples of this. So things like we saw before with that data dependency that was modeled as the flow tensor load, where we had to load the comparison result to then decide if we should continue scheduling, which funny enough might actually be this right here. No, this right here. So yeah, because here's a HAL buffer load. So this is actually loading the value from there. If instead, once we don't have this submit and wait, which this is going to die soon, we yielded here, waiting for that buffer to be ready to read and allowed other work to continue, other invocations to the model, other models, etc. We can keep the GPU full until the buffer is ready, and then the buffer load can continue and then continue on execution. And where this kind of combines with some of the more interesting stuff around dynamic batching and coalescing is we can insert these yield points and kind of collection points wherever we want. And so, for example, if this right here, this dispatch was a giant map mall of, you know, the inner LSTM kind of layer weights multiplied by the current activation, there is a data dependency there. We wouldn't be able to, say, combine multiple of those map malls together because they require the activation from the previous state. But if we wanted to dispatch those all subsequently, effectively turn this into something where there's a bunch of these dispatches to the same kernel with the same weights, we now have a much better chance of exploiting the memory locality of those weights being loaded into SRAM or higher caching levels, etc. If there were no data dependencies, then we also have the ability to start caching here. And when we do that, that'll be modeled as some kind of different IR. There will likely be something like a VM defer that allows a join point for multiple these to come together. But that's later this year kind of stuff. But that's what this will end up looking like when you're thinking about the code that you're actually generating. There won't be some giant system trying to track all of the state and determine what is possible to batch and be very aware of what the model's doing. It's going to be very localized transformations that are effectively looking up at an index table of the number of waiting items at here and or at this yield point, and should it continue, and effectively again get back to no runtime work and an entire class of kind of runtime tracking that doesn't need to exist. Was that helpful stuff?
Yeah, that was what I was digging at for you to explain to everyone else.
And then what we're looking at here, this is pre-canonicalizations that we don't really want to look at, because you can see what we've done as we've been lowering down is those things that were like the executable layout lookups become these global reference loads. All the HAL ops become calls to the HAL module. And then what was the shapes and dimensions and all that stuff have become their expanded ops. And in this case, all of the shapes are constant in this model, but if these were dynamic, these might be, you know, like a mul I32 of some dynamic shape by, you know, the constant size or whatever. And next week I'll have much more interesting examples of that. And I think I sent some along in the mail thread today. But yeah, basically we bake that out. This is pre-canonicalization in CSE, and so you can see almost all of these constants are just the same because a lot of the shapes are the same. Let's see if we can get down. Here you can see all of the state this model keeps. So these are basically all of the different executables as they're cached, and that's it. So again, what would have been just like the size of an STD, unordered map in terms of the code generated for that for your particular type, and then the runtime overhead for dealing with that has effectively become an array of 21 elements that can be indexed with an indexer. So yeah, I'm a big fan of that. All of the binaries for all of the executables have now been embedded, so they just become little read-only data blobs. And again, getting to local, like the kind of continual local optimization in here, it doesn't exist yet, but deduping these is super easy. And so in some cases, we hope that we have already deduped these at a higher level, like way back in the flow dialect when we're looking at executables and they're kind of the same, because we can do more things there. We can say like, oh, these two executables are the same except for the input shape dimensions. So let's make that input shape dimension dynamic. And now we've been able to dedupe both of those executables that otherwise would end up as two completely different compiled blobs into one. And we did that using the information we have available there. We know it's still in tensor form. We can do those kind of rewrites relatively trivially. Whereas like once we're down here and we're basically looking at byte arrays, we can't do any of that. But at the same time, we might still end up with some of these things via the different transformations that happen. And an example of that is like I just added support for string blobs. So you can pass strings as attributes to opts at runtime. And those get outlined, the actual string contents as UTF-8 characters get outlined into these little row data blobs and loaded just like any of these. And so a deduping step on that, now you get effectively the same kind of string table optimizations that you would normally get, linkers to do, trying to deduplicate strings across an entire binary. We can do here as a relatively simple optimization. And there will be other cases with that, with like larger constants for weights or convolution kernels and things like that. This is another example of where there's some missing optimizations. So yeah, all of these are, this is what is generated to kind of cache and compile the executables at runtime. And so we might support multiple formats. These are kind of like format identifier tags. And so at runtime, we have to, given the current device we're using, select which format out of the ones we have available we want to use. But you can see here, we only have one format available. And then all of these select formats are making the exact same call, and this should have no side effects. So for some reason, CSE is not removing this now. But once it does, almost all of this should go away because, as you can see, all of this is just effectively the same repeated non-side effecting IR. And then after the canonicalizer runs, like, actually a lot of that did go away here. So here, this is just calling out to initialize the various layouts. Let's go to the final. Yeah, so I think this is the final function here. Let's go to that readback. Yeah, so here's the readback. So this is after canonicalization. All of those constant values have pretty much folded away. They're probably all sitting at the top here. So that's it. So what was kind of daunting when you looked at it, because there were like thousands of these constants, there's really only a dozen, which is nice. And if, again, these were dynamically computed shapes, those would also get hoisted, because usually you're transposing or collapsing dimensions or something like that, and you don't have like 10,000 different unique shapes within a single function. You usually only have a few, and all those shape computations get CSE'd and moved up to dominating blocks, and effectively, again, the kind of thoughts at runtime where, oh, I got to keep very careful track of all my shapes, and what is the max rank I support on my shapes because I'm packing this into some inline structure, and just all these kind of things don't really exist here, because we've already converted those into the basic math that needs to be performed. We've already elided all of the use of that shape information that is not necessary. And the only places we still have it left are the ones that likely should be removed anyway. So again, we still have these compute sizes that are taking the shapes. These should really not be here right now. But even if they were, these should be deduplicated in a lot of cases. You only need to, for a particular allocator, for a particular buffer, for a particular shape, ask for its actual byte size once, because that's unlikely to ever change for that particular set. So all of the compute sizes should mostly fold away in the same way. And then basically, as we're dispatching, once we've done the folding, it really is look up the executable, push the bindings, dispatch it, insert a barrier. And that's really what this program does. And it has a loop. If you were to hand code this model very carefully, and assuming we get a lot of these optimizations in, but even before we do, if you were to sit and hand code, given the source Python, this model, you would be unlikely to, without a tremendous amount of work, get to this minimal set of operations, because it's just so unmanageable to try to code for a system like Vulkan directly. So you always add layers of abstraction to kind of make it easier to work with. But every time you do that, you're adding additional work on each one of these things. And so pretty much everyone uses some abstraction to insert the barriers for them, some abstraction to track buffer bindings, et cetera. And so this is where kind of our base state, where today, like there's all these super trivial things that are not being done. Our base state is still pretty good. The things that can be improved are like, that do have massive impact are like the formation of the dispatch regions, and what are we, how many dispatch regions do we end up with? What are we putting in there? But again, that's something, if you were doing it by hand, you would be doing that anyway. And the heuristic most people who are familiar with GPUs use is the same one that we're using here, which is kind of group things by invocation count. And so what's cool about this is when looking at this, I only see this getting dramatically better and getting to the point where we can pretty confidently say that there's no work happening here that you would not do yourself if you were sitting down and hand coding the model. Only we didn't have to hand code this at all. Which that's the whole point. And that's it. And so this is runnable. The VM, the serialization from this IR form to the VM is almost 1-for-1 and generated from TableGen. And then the actual VM itself is pretty simple. So it's, if you've ever implemented an emulator in a college class, this is probably exactly what it looked like. Most of this is actually just comments describing what it is doing. But it's really just, you know, add, like, or in this case, this is the unary op, but like here, like this is all of our math. And that's it. And so for the flexibility of deployment that we get by having this interpretable form, and the fact that we're not doing any of the heavy work here in terms of all the dispatches are still happening either in the VMLA case via library calls that are handwritten, or in the case of like the code gen path in generated code, the operations we're performing here really are these relatively, I mean, almost all of them are just calls. And then there will be a very small set performing the shape math up here. And so there's not much benefit, given that we've already been able to run CSE and DCE and folding and constant folding and all that kind of stuff at this IR level, of omitting this as any form that we then take further into a compiler, in that we wouldn't magically become faster by, you know, a non-constant scalar if we were instead omitting the code to do the add of 2 registers in a list, which is why I'm pretty happy with where this is now. And like, even though we could lower this to LLVMIR and generate it ahead of time, we don't have to yet, which is really great. It lets us concentrate on other things. But if you did want to target this on like super tiny embedded ARM core, you could see how you could, like, you could, all of these VM calls become LVM calls, constants become constants, you know, LVM add from VM add, like, and then this should be like, unless you were writing your model, hand coding it in assembly should be nearly what you can get. Hopefully. So, any questions? I have a cat.
So just the cat. You know, when you're seeing the stuff, the one key that I don't know if it was covered that is important is any of the hal.ex instructions are things that are actively load bearing on future features that have not been implemented yet, and are just pulling several things together that really need to be disaggregated. You know, specifically like the submit and x.submit and wait is needs to be properly conditioned on semaphores and other things so that we can hit the concurrency. And there's other cases in here, so you can almost map these one-to-one with issues that for future feature development.
Yeah, and what's nice is with the pending stack of CLs I have, we're down to 3 of those remaining. So one
kind of doozies though.
Yeah, but also things that aren't necessarily required immediately. So like the shared device models a single device, a HAL device that's kind of used. Until we go with heterogeneous, like concurrent heterogeneous execution, a single device is fine. This still gives us the flexibility to target either the LLVM backend or the Vulkan backend. It's only when we want to start mixing those together within the same execution that needs to be fixed. Defer release is going away soon, and submit and wait as well with semaphores. Those basically both go away. And so I will be pretty happy when the last thing we have is kind of the global device handle. And what's nice is the solution to that, to kind of fix that, is mostly there, like having different interfaces for the executables for the different devices, having multiple binaries that can be embedded for the different things. A lot of that's already supported, and there's just very few places that will need to be fixed up. And like specifically what that'll look like is things like, oh, I'm in a totally different window now. What is this IR? I'm not familiar with this. Yeah, what that'll basically look like. So this for example is dynamic shapes. So here's a dynamic element count calculation based on some dynamic shape here, and then the rest of this. There's no multiply constant folding of constant multiplies, which is annoying. But this should basically just be a single multiply out, and that's the extent of our dynamic shape math that's required at runtime. But what this will look like when we have multiple devices where they may, for example, have different memory layouts for each device, is a select between, if there's two devices, a select between the device being used, which byte count is the one that it has. And so it ends up just being a very small set of operations inserted. And in a lot of cases, what we'll likely do in the heterogeneous builds is classify entire flow streams that should be run on independent devices. And then as we're lowering, we can do a lot of the folding. So if we know one device is a CPU device with dense tensors, then we don't need to implement switches every single time one of those tensors is accessed, because we know the scope of where those tensors can be accessed. So it ends up not being as scary as like a total explosion of code of like, you need to now duplicate the entire world. And CSE and stuff, those kind of transformations can help this in a lot of ways. The work group counts will likely end up the same between a lot of these things. If they're using the same executable interface, the binding set should end up the same. And so there really won't be too large of an explosion. There could be, if you wanted to say compile both for a high-end Vulkan device that had an unlimited number of bindings and an unlimited number of push constants and et cetera, arbitrary data type support, versus a min-spec Vulkan device that had a maximum of 4 bindings and didn't support anything but 32-bit floats. Then you might end up with a lot more duplication, but that's also the kind of case where today you deploy different binaries to different devices, right? You don't ship ARM code to MIPS devices on Android ahead of time. You solve that via deployment, as opposed to assuming that one binary will fit every device.
I suspect that there's work hidden behind there, but that also applies to the future too, and probably involves, gets realized with a compiler flag of the form of, a high-level device category or something, or profile that we've defined a compatible set of targets that are reasonable.
Exactly. And then, yeah, the next big thing that's coming after the dynamic shape stuff is done is the submit and wait death. And that will likely end up manifesting as functions that do perform any work will start to get semaphores on them as both inputs and outputs. And what we'd be doing here instead is signaling the semaphore after this command buffer has been submitted to a specific value. And that's what will kind of give us a very explicit way of, if you were calling into this model multiple times, you'd call in, you'd get a semaphore back that will be signaled to, time t when it's done. And then you call back into the model with that semaphore saying, wait until t, and then continue, and you get a semaphore back that says t+1, and then you continue, et cetera, et cetera. And that allows us to then basically give all of that dependency information between those different invocations to the underlying hardware and let it schedule as much as it can. If you're calling into two different entry points of the model that have no dependency on each other, that should be naturally represented in those semaphores having different timelines, and then the device can run those concurrently. And we don't have to keep track of that as a scheduler here generating the scheduling code, and the runtime doesn't have to keep track of that because it has no concept of any of this. It's just merely passing along the values to the actual hardware, which is nice. Improvements to the compiler and our scheduling then have direct improvements on our actual performance instead of then also needing to make sure the runtime is compatible with it, and plumbing a bunch of stuff through there as well. You'll note I'm not showing you anything of the runtime besides this little dispatch loop, because that's really all there is. I guess the other useful thing is this guy, which is the HAL command buffer for the Vulkan side, where just to reiterate, almost all of the functions exposed by the HAL are directly mapped to Vulkan calls. So the extent of our overhead when we're calling into Vulkan is, ignoring the trace scope there, a reinterpret cast and a conversion of enum values. And pretty much all of these are like that. Copy buffer is the same thing. So that's when saying things like zero overhead, like nothing is zero overhead, of course, but compared to what you would write by hand, you would still have to write this by hand. You can't magically get rid of this if you want to perform a copy in Vulkan, and that's the extent of what we're adding on top of the base Vulkan calls.
Ben, how many kind of like virtual type calls are there to get to here? Because I imagine the VM dispatch, when it's doing like the VM call into the HAL module, that's one. And then I guess there's probably one coming into this direct command buffer copy buffer, and then one into the VK symbol. So that's 3 virtual calls for each of these.
Yeah, so these are all dynamically resolved, and always will be. The call, so hold on, cat on keyboard. So the kind of layers that we have right now, and this is very flexible in that way. So this is the actual VM module definition, and so let's just go back to this is the VM call that comes in, and so the extent of what the VM call is doing is basically just marshaling from VM types into our C API. And so here's kind of the first point. It's like, well, if we're doing the interpreted VM stuff, this will have to happen because we have to go from the VM to our own calls. But the way that the HAL API is designed is the C API here could have different implementations. So for example, if you didn't need any flexibility in terms of like the ability to swap in different HAL backends, you could implement a HAL implementation of the C API that just literally called the Vulkan call directly, and then that's it. What we have with the C++ code, though, is basically wrappers that make it nicer to write HAL backends, because then we have nice C++ classes with big types and stuff. And so the C API that we have by default is just calling into those. And so here, this is that abstract command buffer type. There's, of course, once you've compiled and optimized, if you've only linked in a single HAL implementation, there's the possibility of this getting devirtualized. Also, this C API should get inlined if it's not in terms of a full link time optimization, because it's not really doing anything. And so there's the code levels of indirection, and there's the actual indirection at runtime that would happen. And I suspect like these should be pretty trivial to get rid of. And then that's it. So basically we go from VM to our C++ HAL module. We go through the C API into the concrete C++ class. And again, this is really just there for flexibility. There's nothing that the HAL module is using that is not exposed through the C API. So if you did, for an embedded device or something like that, want to just have the implementation there, then you could get rid of all that overhead. And if we were code generating, instead of doing the VM interpreter, you could generate the code so that a VM call to the HAL command buffer fill, like literally emitted a call to the C API. And now you can remove this level of indirection. My hope is we can avoid doing that for a while so that we just don't have too many things to deal with until things settle down. But there is that possibility.
Any other questions? Okay, thanks everyone. I'm going to stop recording now.